Welcome back to Stem Cells Unveiled from Basics to Breakthroughs. I'm Dr. Sukant Khurana, your host and a neuroscientist. We are on episode 6 Brain Games, Stem Cells in Neurology. Leading us today is once again brilliant Basudha Banerjee, a regenerative medicine expert who's been driving this series with unstoppable energy. Basudha, take us into the brain. I'm ready for this one.
Dr. Khurana, this is my favorite territory yet, stem cells and the brain. It's where science meets wonder. The nervous system is so complex, and the stem cells are opening doors to tackle a lot of neurodegenerative diseases, repair spinal cord injuries, and even grow mini brains for research. I am buzzing to dive in. So let's start with neurodegenerative diseases like Parkinson's and Alzheimer's because these are brutal conditions. So, Dr. Khurana, as your expertise as a neuroscientist, what's your opener on how stem cells might help here?
Well, you're leading the charge, Vasudha. I'm all in. For me, it's about replacing lost neurons like dopamine producing cells in Parkinson's. Stem cells could be the key. Over to you.
Perfectly put. Parkinson's is a classic. Dopamine neurons in the substantia nigra die off, causing tremors and stiffness. Now, stem cells, especially iPSCs, can be turned into dopaminergic neurons in the lab and then transplanted into the brain. I have read a lot of trials where patient got these cells and saw some motor improvements. It's not a cure it, but it's very promising. Then we also have Alzheimer's, wherein amyloid plaques form and neuron losses wreak havoc. Here, stem cells might not just replace the neurons, but also deliver growth factors like brain derived neurotrophic factor to support the surviving cells. I've seen iPSCs derive neural stem cells reduce plaque in mouse models. That seems like a very mind blowing stuff. Dr. Khurana, what's your take on these mechanisms?
Yeah, it's dual action that gets me replacement and support. Trophic factors from stem cells could slow degeneration, while new neurons could rebuild circuits. It has huge potential. My biggest gripe, I think, and I occasionally right, not always right. I'm glad I was sort of right on the challenges from 2000, even before I started working on mammalian brain from 2000 to 2003. I was working on insect brain. That was my start from Bangalore NCBS with Ovid Siddiqui. I used to argue with some people who were interested in Parkinson's back then about new neurons, even if stem cells can one day fill in that. Um, how would they go? Because in embryonic growth, they are filling in a relatively empty space while the wires are already laid out. So finding new route is challenging. And I'm seeing we have come a long way from there, even though my instinct on the challenges, some of the challenges were right. And I'm pleasantly surprised. I was going through some of the old emails with friends on those challenges back then when I'm not even sure if Yahoo Mail people use it then. But I've saved some of those things with fellow friends who were back in Bangalore at that time in NCBS and are now in different corners of the world, but had very interesting, intellectually stimulating environment. But I'll get back to what I just said, that what really gets me is dual action. It's not just replacement, but it's even the support. Trophic factors from stem cells can really slow degeneration, while new neurons rebuild circuits. So these two are fundamentally two different things happening in one through stem cells. That's really huge potential that I see. Over to you, Vasudha.
Yeah, I mean, it's also not just about adding cells. The brain's microenvironment matters a lot. Stem cells, they tweak inflammation too, which is a bigger driver in these diseases. So now let's shift to spinal cord injuries, which is another beast. The spinal cord does not heal like the skin. A lesion cuts off the nerve signals, leaving people paralyzed. So stem cells could probably bridge that gap. Neural stem cells or say mesenchymal ones, they can be implanted into the injury site. I've read lot of studies where they form scaffold, encouraging the axons to regrow. Even in animal models like rats, transplanted oligodendrocyte precursors even remyelinate the nerves, restoring some movement. It's early, but I get goosebumps honestly thinking about all these human applications. So, what is your lens on the spinal repair?
Yeah, so you're painting an incredible picture, Basudha. I would say is the combo stem cells not only regenerate but reduce scarring and inflammation, creating a healing niche. It's a tough challenge. It's a very tough challenge now.
Yeah, I completely agree. It is tough, but it is thrilling. So the challenge is integration of those new cells. Those new cells need to wire up correctly, and the injury sites hostile. Still, trials are pushing forward. There is one with human embryonic stem cell derived progenitor that is showing leg strength gains in the patients. Restoring neural function is not just about movement, either with sensation or autonomy. I'm sort of obsessed with how these stem cells could rewrite all these outcomes. Now, we come to the point where it gets little wild, brain organoids. So these brain organoids are mini brains that are grown from iPSCs. They're like tiny 3D clusters mimicking the brain structures. It's surreal. It's like a pea-sized brain pulsing with the neurons. Dr. Khurana, what are your thoughts on organoids?
Well, that's a neuroscientist's dream. I'll in fact refer to something which is headed in that direction, and I published, I believe, in 2013 or 12. That you can age me. That is some, when you're fresh, you can tell which year you published in. So I, along with Ben Kelly was my collaborator, a computational guy from UT Austin, who eventually, after Columbia, went to work for my MasterCard, quit neuroscience, and is making good money through his AI and data science. But he was sort of the tech engineer in house for a lot of animal tracking computational work. And we wrote a paper together. It was a review on brain slices. And what we were trying to aim at is how can you have thicker brain slices so that you can actually have more of neural circuitry rather than thin brain slices, which people use in electrophysiology to record, and how those thicker brain slices start acting as mini brains. Can you have real brain rhythms in those thick brain slices or slabs? Um, and the paper wasn't cited much, and suddenly, off late, I see a lot of stem cell biologists, organoid people, now suddenly citing that paper that we wrote from Gold Spring Harbor, and I think for 5 years, zero or one citation, something. Right. And I think suddenly people have discovered a gold mine that, okay, yeah, if you have a bigger brain, you're not just talking on neurons. I'll check after this conversation with you where it is at right now in terms of citations. But we were looking at how bigger recapitulation of more brain functions is important. Now, think from neurodegeneration, whole organoids, right? Having modeling brain development or testing drugs, that in brain tissue is revolutionary. I can keep talking, but I would like I would like to see sort of fresh energy or someone who's closer to bench work than me, who's now more of an entrepreneur putting teams together. So I want your perspective on this.
Yeah, I mean, a revolutionary does not even cover it. So you start with iPSCs, wax them into neural progenitors, and then let them self organize. And suddenly you have got a cortex like layers, even electrical activity. They are gold for research. Think of studying autism or Zika effects on fetal brains. Drug testing, even that is huge, like screening compounds on organoids, beats animal models, hands down. I've also seen and read a lot of papers where Alzheimer organoids with plaques and tangles. The real pathology in dish, but the catch is that they lack blood vessels and full complexity. But of course, the potential is still growing, and there is patient-specific many brains to tailor treatments. What limits do you see, Dr. Khurana?
Yeah, I see a lot of things. Vascular issue is a very big one. Without blood flow, they can't scale to full brain size. Still, it's a tool, and they are unmatched for precision medicine.
Yes, so precision medicine, that is the future I see. From Parkinson's transplants to spinal repair to organoids, unlocking a lot of brain secrets. So, stem cells are rewriting neurology. The hurdles like integration, scale, they are real, but the pace of discovery, that is lightning fast. Dr. Khurana, thanks for letting me lead this. It's been a big blast geeking out over the brain. Thank you so much.
Yeah, thanks a lot. You've been phenomenal, Vasudha. Blending passion with expertise seamlessly. I'm sure you'll go a long way in regenerative medicine. That's episode 6, folks, led by incredible Basudha Banerjee. Next time, we tackle stem cells and cancer. Um, and if you got questions, please comment. And it was pleasure having Vasudha once again. And it was really, I'm thankful for every listener to this podcast. We are not just trying to do science, we are trying to build a movement here by combining citizen science that has been my thing ever since 2007 or 8 when we started with 70 people, and now I've worked with thousands of people to try to have science as part of people's lives and not just something people do after PhD or during PhD. So I would like to have more interaction with everyone, people's comments, feedback. And if you think we are going too technical, please ask us. If you think you would want to hear more technical stuff, please write that in comments. We'll really appreciate your feedback. Thank you.